of the hour, so let's go ahead and get started so that our speakers have the full time. I want to welcome everyone today to the symposia on recent advances in research on children's and adults' arithmetic strategy use. We're excited to hear all of our speakers today, and with that, I'm going to hand it over to Koen to introduce the rest of the speakers.
Thank you. We have foreseen 4 speakers in this symposium. The first speaker will be Marian Hickendorff from Leiden University, then Dowker from Oxford University. The third talk would normally have been given by Elke Sekeris from KU Leuven, but since she has left academia, I will take over from her. And the final talk will be presented by Lemaire from the Université Aix-Marseille. So I will immediately give the word or the floor to Marian with the first talk on students' flexible and adaptive strategy use in subtraction problems.
Yes, thank you, Koen. I hope I've started sharing my screen now in the right way. Can you see it? The PowerPoint?
Yes.
Okay. So my talk is about a study into students' flexible and adaptive strategy use in subtraction problems, focusing on the difference what students know and what they spontaneously show. And the main construct underlying this is adaptive expertise, which involves that problem solving is important, doing mathematics, and concepts like creativity, flexibility, and adaptivity are important things to strive for in contemporary mathematics education. And striving for this adaptive expertise in students is important because it's an indicator of deeper mathematical understanding, and it's a key aspect in the development of later mathematical competence. And also, I'm from the Netherlands, and in our Dutch primary curriculum, it is, well, not in the word adaptive expertise, but clever solving arithmetic problems in a clever way is part of our curriculum. So we also, it's also on the formal side of math education. So I'm focusing on subtraction, problems like this, 84 minus 67. And as you probably all know, there are different ways to solve such problems. And I'm focusing on universal strategies versus task-specific strategies, or also called shortcut strategies that are efficient for particular tasks. And I distinguish 2 universal strategies: the sequential or jump strategy, where you sequentially subtract the 67, you split that in 60 and 7, but you keep the 84 intact. Whereas in the other universal strategy, which is the split or decomposition strategy, you decompose or split both numbers. And as you can see from in this example, you end up with 4 minus 7, which you cannot do, so you have 3 short. So of course that causes trouble in kids. That often leads to errors in kids' solutions. So these are the universal strategies that could potentially work on all kinds of problems. And for the task-specific or shortcut strategies, we focus on the first one, indirect addition or subtraction by addition strategy, where you start from the second number and add on towards the first one. So you start with 67 and you add 3, you're at 70, and then you add 14, and you're there. So and the advantage of that is that you don't have to do any subtractions. And this is particularly efficient for problems where the 2 numbers are close together. So that you have to make only small jumps to get there. And the second task-specific strategy is the compensation strategy, where you round to the second number. And then of course you have to compensate for that you have subtracted too many. So you round 67 to 70, and then you have to compensate to 3. And this is particularly efficient for problems where the second number is close to a round number. So for instance, the digit is a 9. So the current example is not the best example. So with universal strategies and task-specific strategies that we focus on. Going back to the adaptive expertise in arithmetic, for my definitions I focus on 2 things: flexibility and adaptivity. And my definition of flexibility is that is strategy variety, using various strategies. And my definition for adaptivity is that you also select the optimal one from your repertoire of different strategies. And of course, the question is optimal with respect to what, because you can look at that from at least two different perspectives. A strategy can be optimal for a given task, like the task-specific shortcut strategies. But the individual performance also matters. If a student does not know, cannot work with the compensation strategy, then that might be the strategy that is best for the task, but not for the individual student. I list these definitions because, of course, different definitions are used in the literature. These are the ones that I use. And what the next step is that from the literature, we know that students are not much inclined to use different strategies, particularly when they have learned a standard approach like the digit-based algorithm. They tend to do that quite consistently. But we also know that they seem to know more than they show. When you ask them in different ways, for instance, can you solve the same problem with more than one strategy? They can do more than they have done spontaneously. So there seems to be some hidden potential there. And that is, so I refined my two main constructs, flexibility and adaptivity, in two subcomponents, a potential part and a practical part. So the most broad thing is potential flexibility, that students know different strategies. And as a subpart of that is practical flexibilities, that they actually use different strategies. And also for adaptivity, I have, I stipulate that there is also potential adaptivity, that students might know the appropriateness of strategies, but not necessarily use the most appropriate ones. And where this all comes together is practical adaptivity, that they actually use the optimal strategy. So this is the theoretical framework that I started from. And what I did is I wanted to measure that in kids. That is basically what this study is about. Well, it's part of a broader research project where I do studies at different curriculum levels. So it goes from the intended curriculum, from goals and standards, to textbooks, to the implemented curriculum, what happens in the classroom, and to finally the attained curriculum, what students really do, the student outcomes. And the main talk of today is about this, my first study in this broader research project about what students do in this field of flexibility and adaptivity in subtraction. And in another study, I'm trying to gain more insights into the opportunity to learn. So what happens in the classroom and in textbooks. And finally, I want to integrate these and relate the opportunity to learn to what students do. That's work for the future. So this study I present today is, I want to know what, I focus on third graders, what they know and show regarding different strategies to solve multi-digit subtraction problems. So that is potential and practical flexibility, and regarding which strategy is optimal. And that is also the potential and practical part, but also I focus on the task perspective and the individual performance perspective. And I have made tasks for all model components of these four constructs. There were 147 third graders participating, and the four strategies that I presented before were focal. And for each strategy, I had a problem type that fits best. So for the jump strategy and the split strategy, for split strategy, the main characteristic was that there was no shortage. For the compensation, that you can easily round to second number. And for the indirect addition, that the two numbers are close. So these were the task-specific shortcut strategies. For practical flexibility, I had them solve 8 problems in their own way. And they hardly ever use different strategies, 1.17 strategies per student. And for potential flexibility, I had them solve the same 8 problems in different ways, and also complete 4 strategies, of which the first step was given already. And I don't have much time to elaborate on this, but they knew more strategies than they used spontaneously, or 1.82. And for practical adaptivity, I looked at the problems designed for indirect addition and compensation and looked at how often they solve this with that particular strategy. And it was hardly ever. They never used indirect addition and compensation. But if I showed them a problem with 4 worked out examples and asked them which strategy is the best for this problem, they could. Not really often yet, but still more than what they did spontaneously. And finally, regarding the adaptivity to individual performance, we first need to know which strategy is optimal for a particular problem. And what I did for that is we focused on 2 strategies, the one that the student used spontaneously and the shortcut strategy that is optimal from the perspective of the task. And I designed a personalized choice, no choice method where students had to solve the same problem twice with each strategy. And we coded speed and accuracy to determine the optimal strategy, the fastest strategy leading to the correct answer. And on the indirect addition problems, that was the indirect addition strategy only 22% of the times, whereas their own strategy was optimal 61% of the time. And on the compensation problems, it was more evenly spread, but still, it's not like the compensation strategy is the best strategy for individual children. I'm running out of time a little bit, I notice. So I will speed up. They use their optimal strategy, but they also use their non-optimal strategy quite often. I'll skip this. So in conclusion, their level of practical flexibility and adaptivity was rather low, but there was hidden flexibility potential. They knew more strategies than they used spontaneously. And they also did know more about the shortcut strategies than they showed. So there was also hidden adaptivity for task-based adaptivity, hidden potential, sorry. And I think the final point is quite interesting, that the task-specific shortcut strategy was not optimal for most students. So a shortcut strategy is not necessarily an easy strategy, and they might not use these strategies because for them, they're not that efficient, but there is also some hidden potential in that. I will skip this. And here, sorry for the hasty end. Thank you for your attention. I don't know if there's time for small questions. Not so much, probably.
We still have time for 1 or 2 short questions.
Okay.
Can I ask a question?
Sure.
Yes, as someone who works in, also works on strategies for addition and subtraction, though I'll only be talking about addition on this occasion, I was wondering if you sometimes find that kids use strategies that are appropriate for addition and overextend them to subtraction. That is, for example, assuming that if 23 minus 6 is 17, then 23 minus 7 must be 1 more or 18, because 7 is 1 more than 6.
Yes, those things happen. What I also think is that the use of the split strategy is usually not that good an idea for subtraction problems. So, but I think they overextend it. They've just have been taught that works pretty well for addition, and then they generalize that to subtraction problems as well.
Thanks.
Okay, then we will move on to the next speaker, which will be Dowker, and she will talk about young children's use of derived facts strategies. And I will share my screen to present Anne's talk.
Great. So yes, this will be about children's use of derived fact strategies, i.e. using a principle such as commutativity, for example, plus a known fact to solve a new fact. So if we could move to the next slide. So perhaps one of the most crucial aspects of arithmetical reasoning is indeed the ability to derive and predict unknown arithmetical facts on the basis of known facts by using arithmetical principles such as commutativity, associativity, and the addition, subtraction, inverse principle. Next slide, please. So without this ability, children would depend entirely on the facts that they've already learned and possibly on rigidly applied, partially understood algorithms, and will be unable to go beyond them independently. For moreover, a complete inability to derive unknown arithmetical information from known information would seem a priori to imply a lack of understanding of the connections and interrelationships between individual number of facts and arithmetical properties. So there's likely to be a bidirectional relationship between use of direct derived fact strategies and understanding of arithmetical relationships, or alternatively of the lack of these. Next slide, please. So in the present study, we investigated 6- and 7-year-olds' ability to use derived fact strategies. The studies investigated them for both addition and subtraction, but due to time constraints, I'll talk only about addition in this talk. And they were using the strategies based on a range of principles, and the principles were selected for their applicability over a fairly wide range of difficulty. Next slide. So one strategy, one principle that we looked at is one that's so obvious that it often isn't looked at, which is the identity principle, which we investigated, in fact, for both addition and subtraction, but again, I'll talk about it just for addition. It's the most basic of arithmetical principles, which is that if an arithmetical principle, if an arithmetical operation produces a given result, then the repetition of the same arithmetical operation will produce the same result. Its use in predicting the result of an arithmetical operation is, properly speaking, not a derived fact strategy, but a same fact strategy. But without this basic principle, it's unlikely that one will be able to use derived facts. And its inclusion in the study is whether it was intended to investigate whether children tend to use the result of one operation to predict the result of another at all, over and above the particular principles that they're able to use in such predictions. Next slide. So we also looked at the commutativity principle. For example, if 8 plus 6 is 14, 6 plus 8 is also 14, and it's a crucial principle for addition. It doesn't hold, of course, for subtraction. Next slide, please. So we looked at simple associativity-based strategies involving the addition and subtraction of 1. And the n+1 or addend +1 principle for addition is the simplest of the assumptions that result from the broader associativity principle. And this is the principle that if one of the addends is increased by 1, then the sum will also be increased by 1. So that, for example, if 8 and 6 is 14, 8 and 7 will be 15. If 23 plus 44 is 67, 23 plus 45 will be 68, etc. Next slide. And the n-1 principle for addition, or addend -1, is similar. If one of the addends is decreased by 1, then the sum will also be decreased by 1. So that, for instance, if 46 plus 32 is 78, then 46 plus 31 will be 77. Next slide. And then there's the addition, subtraction, inverse principle. That is, if you know that 3 and 7 is 10, 10 minus 3 must be 7. If you know that 36 minus 13 is 23, then 13 plus 23 must be 36, etc. And most studies have suggested that strategies based on the addition, subtraction, inverse principle, so in algebraic form, if a plus b minus b is a, or if a plus b equals c, then c minus b equals a, are among the later developing derived fact strategies and are not typically used till the age of about 10. However, Berudi et al. In one of the first studies of derived fact strategies in kids, 1983, found that many 7 and 8-year-olds used this strategy, and that it typically preceded the n+1 strategy. And some recent researchers, such as Gilmore and Bryant and Robinson and Dubé, found considerable individual differences in elementary school children's use of this strategy, but found that some 6 to 9-year-old pupils used it effectively. I mean, my earliest observation of it is a child of 4 years, 9 months, who was asked what's 6 minus 3, and she said 3 because 3 and 3 is 6. But that, I think, was by any standards very unusual. Okay, next slide. So in the present study, 144 children ranging from 6 years to 7 years, 11 months were tested individually. They came from 2 state primary schools in Oxford. 79 were boys, 65 girls, and mean age 81.95 months. So on average about 6 years, 10 months. Next slide. So in order to evaluate the children's competence in addition calculations, a mental calculation task was given to each child. It consisted of a list of 20 addition sums graduated in difficulty from 4 plus 5, 7 plus 1, etc., to 235 plus 349. And these sums were simultaneously presented orally and visually in a horizontal format, and the children's answers were oral. And the children were then divided into 5 levels according to their performance on the mental calculation task, with the aim of giving children problems that would be too difficult for them to be, just too difficult for them to solve unaided, but which they might relatively easily be able to do using the principle. Next slide. So the levels of addition performance were beginning arithmetic, unable to deal reliably with single-digit addition. There were 11 children in this group, and since all the children in the group were over 6 years old, at least in year 2 at school, the children who were at this level were children who were struggling quite a bit with arithmetic. Then the facts to 10 level, where they could add sums where the solution was 10 or less, but failed with most larger sums, where there were 34 children. The facts to 25 category, where they could add sums where the solution was 25 or less, but failed with most larger sums. 2-digit, that's 63 children, the commonest in this group. Then 2-digit addition, no carrying, where they could add 2-digit numbers where carrying wasn't required, but mostly failed with sums where carrying was required, where there were 16 children. And 2-digit addition with carrying, where they could add 2-digit numbers, but mostly not 3-digit numbers where carrying was required, where there were 20 children. Next slide, please. And the children were then given an arithmetical reasoning test involving use of arithmetical principles in derived fact strategies. The technique was used of giving children the answer to a problem and then asking them to solve another problem that could be solved quickly by using this answer together with the principle under consideration. For example, a child at the at the facts to 25 stage might be given the problem, might be told that 44 plus 23 is 67, and then asked to add 23 plus 44. And problems preceded by answers to numerically unrelated problems of similar difficulty were given as controls. Next slide. Next slide, please. Yes. So the exact arithmetic problems given varied according to the previously assessed calculation level of the child, were selected to be just a little too difficult for them to solve unaided, and the principles were those described above: identity, commutativity, addend +1, addend -1, and addition, subtraction, inverse. Next slide. And the children were also given the whisk arithmetic subtest, but this won't be discussed in the present talk. Next slide. So this is a table. I mean, you don't need it for to go over it in detail now, but it gives the levels, problems within the range, problems just outside the range, the numbers of children involved, their mean age in months, which slightly increased for level, the mean arithmetic scaled score, which increased considerably for level, and the percentages at each stage and altogether that used each of the principles. And I can send a copy to anyone who's interested. Next slide. So many 6- and 7-year-olds could use some derived fact strategies, but it varied both with the child's calculation level and with the particular strategy. Most who were beyond the beginning arithmetic level used identity, but it's interesting to note that most at this very beginning level, at least those who were low attainers compared with their peers, didn't, but most beyond that stage did. Most at the facts to 25 level or beyond used the commutativity and addend +1 principles. Many at the facts to 25 level and most at the higher levels use the addend -1 principle, but rather strikingly, the use of the addition, subtraction, inverse principle was rare even at the highest levels. Next slide, please. So to conclude, use of each principle increased with calculation ability. I will say that except for the addition, subtraction, inverse principle, which was difficult for everybody, that the arithmetic scaled score also was also associated with use of principles. The fact that the use of each principle increased with calculation ability was true despite the fact that the difficulty of the arithmetic problems given was adjusted according to the children's calculation performance. So even when you gave children problems just too difficult for them to solve spontaneously, they were still more likely to use principles if they were at a higher calculation level. Some principles were much easier than others, notably identity and commutativity. And in particular, most children, even at the higher levels, didn't use the addition, subtraction, inverse principle, despite the fact that children at this time have been explicitly taught it as part of the national curriculum. And teachers tend to comment that it's a difficult one for many children to acquire. But on the other hand, they were mostly using the commutativity principle and the addend +1 principle. Okay, so are there any questions?
Okay, David, maybe just one short question, if possible.
Yes, I apologize if I'm hard to understand because there's some background noise here. Thank you for a great talk. I have a question about the finding that use of principles increased with calculation ability. I can think of at least two possible explanations for that finding. One is a direct effect of calculation ability leading to greater knowledge of principles and thus greater use of them. The other is an indirect mechanism in which greater calculation ability frees up cognitive resources, making it more possible for children to reflect on the strategies they know and thus increasing the use of alternative strategies. Do you have any thoughts about those two possible explanations?
I think probably both are involved. There's also a third explanation, which is that knowledge and use of principles increases calculation ability. So I think all of these are involved, and that children who have difficulty with calculation do often get rather bogged down in one or two particular strategies, often counting strategies, and this may be a kind of vicious circle.
Thank you.
Okay, thank you. Then we'll move on to the next presentation, which will be given by myself. The title of this talk is The Early Development of Children's Strategy Use in Computational Estimation. So computational estimation can be defined as providing an approximate answer to an arithmetic problem without calculating it precisely. And computational estimation is a mathematical skill that is often used in our daily life. For example, we will rely on computational estimation when we want to split the bill among friends after dinner. And it is assumed that complex estimation involves a complex interplay of various types of mathematical knowledge and skills, such as arithmetic knowledge and skills, which are necessary to mentally calculate, procedural knowledge, such as knowing how to round to the nearest number, conceptual knowledge, such as knowing that several answers can be correct, or that there are multiple ways to arrive at an estimate, and also number sense, having a good insight in the relation between numbers as well as in the relation between numbers and their operations. Now, very few studies have investigated children's computational estimation below the age of 8 years. And the few that did so found that young children are already capable of simple computational estimation from 5 years onwards. However, very little is known yet about young children's computational estimation strategy use. But we do know from research in older children and adults that there are 3 types of what I will call genuine computational estimation strategies. And a first type of genuine computational estimation strategies are the so-called reformulation strategies, in which the operands of the problem are changed into a mentally more manageable form. So the typical example is the rounding down strategy. The second type of strategies are the translation strategies, in which the operation itself is changed into a more manageable form. For instance, this addition can be changed into a more easy multiplication. And a final group of strategies are the so-called compensation strategies, in which adjustments are made for distortions that result from a previous reformulation or translation. Interestingly, it has also been found that upper primary school children sometimes rely on exact arithmetic to solve computational estimation problems. And they sometimes even calculate the outcome exactly and adjust it afterwards to make it look like an estimate. Now, with the present study, we wanted to investigate the longitudinal development of young children's computational estimation strategies from 1st to 3rd grade of primary school. And we focused on the changes in the strategy repertoire, the changes in strategy frequency, the changes in estimation performance, and the relationship between strategy use and performance. Our sample consisted of 316 children, which were tested at 3 time points, each time when in the fall period when they were in grade 1, grade 2, and grade 3. And these children had to estimate the outcome of a number of addition problems that varied in difficulty. So these were the problems that we presented to the children. And as you can see, in grade 1 and grade 2, we presented exactly the same problems, but for grade 3, we presented problems of which the difficulty level was increased. This was done to prevent that children from grade 3 would just simply solve these problems by means of exact arithmetic. So actually, there were only 4 problems that were presented at the 3 time points. So at each time point, we started with a warming up game in which we familiarized children with the concept of computational estimation and its related vocabulary. And next, we presented them with the estimation problems on a computer screen. And these were also read out aloud by the experimenter, and children had to provide their answer orally. Immediately after each trial, we asked the children to explain to us how they came to their answer. The strategies were classified according to the following scheme, and I will limit myself to these 5 broad strategy categories because in grade 1 and also to some extent in grade 2, a lot of verbal reports were in the rest category. So the first category here are the problems that were solved by means of exact arithmetic. The second strategy was exact arithmetic and then adjusting the answer. And the third category were the so-called rudimentary computational estimation strategies, in which the children not really explained how they came to an answer, but they merely gave a description that indicated some emerging conceptual understanding of computational estimation. For instance, one child said, "I estimated what would be close to the real sum." The fourth category were the general computational estimation strategies that I outlined before. And then we had a rest category in which we put all verbal reports in which children said, "I don't know what I did," or "I cannot explain," or "I simply guessed." So let's have a look at the results. First, we looked at the size of the strategy repertoire, so the number of strategies that children mentioned, and we noticed a significant increase from grade 1 to grade 2. This increase went a bit on, but it was not significant between grade 2 and grade 3. Next, we looked into the strategy repertoire and more specifically what strategies children used. So you see here the proportion of participants that mentioned at least one of these strategies once. So if we look at the exact arithmetic strategy, we noticed that there was a significant increase in the number of children that reported strategy from grade 1 towards grade 2. We also found a significant increase in the number of children that reported exact arithmetic and adjustment between grade 1 and grade 2. And for rudimentary estimation, there was first a significant increase in the number of children that reported that strategy, after which it decreased again from grade 2 to grade 3. Perhaps the most interesting result is the one with respect to the genuine estimation strategies, which were hardly mentioned in first grade, but the number of children that reported strategy increased significantly towards the second grade, and we observed an even stronger increase from the second towards the third grade. For the rest category, we saw a significant decrease in the number of children that mentioned one of the strategies belonging to the rest category. Next, we looked at the frequency of strategy use, so the proportion of trials on which a strategy was used. And we noticed that for exact arithmetic, there was a significant increase on the number or the proportion of trials on which this strategy was used from grade 1 to grade 3. There were no changes in the frequency of use of the exact arithmetic and adjustment strategy. And we noticed a significant decrease in the use of rudimentary estimation from grade 2 towards grade 3. Genuine estimation was used significantly more frequently in grade 3 compared to grade 2 and grade 1. And also the use of the rest strategies decreased significantly with increasing age. This was calculated on all items, but since the items that we used in the third grade were different from the ones in first and second grade, we wanted to be sure that there was no confound by the use of these different items. So we did the same analysis only on these items that were common to the three testing moments. And as you can see, the picture is almost identical. Next, we looked at the accuracy, which was measured in terms of the percentage of absolute error, meaning the higher the PAE, the less accurate the estimates were. And prior to conducting this analysis, we also removed all exact answers from the dataset as to have an idea of the accuracy of children's estimation capabilities. So as you can see, there was a significant decrease from grade 1 towards grade 3 in PAE, and it further decreased significantly from grade 2 towards grade 3. Finally, we calculated the correlation between the PAE and the frequency of use of the respective strategies for each grade respectively. And as you can see, for exact arithmetic, we observed significant negative correlations between the frequency of use of that strategy and PAE, meaning that the more children used exact arithmetic, the more accurate they were, which is kind of logical. The same holds for exact arithmetic and adjustment in grade 2 and grade 3. And also for genuine estimation. So also here we found a significant negative correlation with PAE in grade 1 and grade 3, meaning that the more frequent children use one of these genuine estimation strategies, the more accurate they were. For rudimentary estimation, we did not find any correlation with accuracy. But in grade 3, we found that there was a positive correlation with PAE, meaning that the more children used rudimentary estimation, the less accurate they were. And the same holds for the use of the rest strategies in each of the 3 grades. So to conclude, we observed an age-related increase in the number of strategies that children used, and this was mainly due to the adoption of exact arithmetic and genuine estimation in the strategy repertoire. There was an age-related increase in the use of exact arithmetic from grade 1 to grade 2, and in the genuine estimation from grade 2 to grade 3. at the expense of rudimentary estimation and the strategies belonging to the rest category. Or stated differently, as children grew older, they tended to use more frequently more sophisticated strategies, and the less sophisticated strategies were used less frequently. We also observed that the more frequent use of exact arithmetic with or without adjustment, but also of general estimation, led to greater accuracy. So to conclude, the children already understood some principles of estimation at a younger age than is generally taught, which was witnessed by the fact that they adjusted their answers after having calculated them exactly, and also by the reference towards the proximity principle when they reported a rudimentary estimation strategy. However, the use of the real computational estimation strategies seems only to start off from third grade onwards. Thank you for your attention. Are there any questions? Maybe one short question. Yeah, Marian.
Yes, thank you, Koen. I was wondering if children ever combined exact arithmetic and genuine estimation, or was it for individual kids that they used either exact arithmetic or genuine estimation strategies?
They used both of them, and it was also affected by the size of the problem, of course. So on the small problems, they tended to use more exact arithmetic, and on the larger problems, they tended to use the genuine estimation.
It's actually quite flexible, I would say.
Yeah, indeed.
Yeah. Okay, thanks.
Okay, thank you. Then we will move on over to the last presenter of today, which is Patrick Lemaire, and he will tell us something about emotion and arithmetic and the role of strategies therein.
You're still on mute.
Patrick, we can't hear you.
Can you hear me now?
Yeah.
Okay. I just wanted to say thank you, Koen, for putting up together this nice symposium. Ever since Bob Siegler alerted us on the importance of looking at strategies, I think the field has improved a lot, has addressed very important issues and gained very deep understanding, not only in arithmetic, but in other mathematical cognitive tasks and even other cognitive tasks. Today, I'm going to illustrate the usefulness of adopting a strategy perspective to look at the interaction between emotion and arithmetic. Recall that the research in arithmetic has two main goals, one empirical, one theoretical. Empirically, we want to determine which factors influence arithmetic performance, and theoretically, we want to decipher the underlying mechanism responsible for these effects. Empirical research has shown that we know now arithmetic performance is influenced by a number of factors like problem, situation, or participants' characteristics. Today, I want to bring up some data that documents the role of emotions. Theoretically, research has shown that arithmetic is involving both domain general and domain specific mechanisms. And this has been evidence in research adopting a strategy perspective as well as in other research. We want to know how emotions influence arithmetic performance if they do so. And today I'm going to report some data that speak to these issues. We have to take into account general research on emotion and cognition when we want to understand how emotions influence arithmetic. In this recent book, I reviewed the state of the art in a wide variety of cognitive domains. And what we usually find is, whatever the domains, you find research reporting both impairment of cognitive performance as well as improvement under emotions relative to neutral conditions, whatever the domains that you look at. So what about arithmetic? Well, in arithmetic, surprisingly, there has been just a little or too few research. However, we have a few evidence that emotions, especially negative emotions, influence arithmetic performance. This evidence comes from both correlational approaches and experimental approaches. To cite an example, correlational approach studies, work on math anxiety have shown that there is a fairly significant correlation between math performance and math anxiety, ranging from 28 to 48, as Anne has reviewed most recently fairly exhaustively. There are also some evidence coming from experimental approaches, whether they looked at directly or indirectly at the issues of how emotions influence arithmetic. From indirect evidence, we can cite effects of social pressures, for example, or effects of prior task, failure or success. But there has also been some direct evidence where people have tried to experimentally manipulate or induce emotion in participants. To just give you an example of research, let me cite one recent work of ours where we look at this issue by asking people to verify arithmetic problems the following way. I use this so-called within trial emotional induction procedure in the present experiment, so I can spend a few seconds here to explain it. For each trial, participants were shown a ready signal for 1500 milliseconds, and then they were shown a problem superimposed on an image that is known to trigger either a negative emotion or a neutral emotion. These images are coming from the Aix-Marseille databases. The images can be presented slightly before or together with the problem, and participants are asked to be as fast as possible to say whether the presented equation is true or false. Now, what we found with Camille Allemand, a PhD student of mine, is deleterious effects of emotions on arithmetic performance, whether people are asked to solve simple arithmetic problems or more complex computational estimation problems like Koen has just introduced here. You can see when you compare young and older adults, young adults are influenced by negative emotions when they solve simple problems, whereas older adults are not influenced. But both groups are influenced by emotions as they take longer to solve those complex arithmetic problems under emotion conditions here in white, compared to neutral emotion condition here in black. You see that young adults increase by 721 milliseconds, whereas older adults increase by 450 milliseconds under emotion condition. So we found some deleterious effect of negative emotions in arithmetic problem solving tasks. We found that older adults are less affected by negative emotions. And of course, the next issue is what are the responsible mechanisms, both for the effects of emotion and for age-related changes in emotional effects. I have some data in children that I'm not going to present today. Those of us who are going to go to Belgium in June will see those beautiful data in children, so please come to Antwerp. I'm going to present the data in young and older adults. To account for the effects of emotion on cognition in general, but on arithmetic performance in particular, I just rely on a very simple and original hypothesis that I call the strategy hypothesis, and that I have already used to account for cognitive aging in this previous book of mine, where I overview a number of findings consistent with this hypothesis. This hypothesis is simple. It just states that emotions influence cognition via strategic variations. So everybody knows now the few strategic dimensions that can be looked at. The idea is that negative emotions may change strategy repertoire, strategy distribution, strategy execution, or how we select the best strategy on each problem. And today I'm going to report data that are consistent with some of these predictions. So in the first experiment conducted to test this hypothesis on strategy repertoire, we use this procedure. Participants saw a blank screen, and then they saw a picture that could be emotionally negative and neutral for 600 milliseconds, and then superimposed to this picture, they saw two-digit addition problem, and they had to give an exact answer to this problem as quickly as possible. And then they saw a blank screen, and then they saw another image. They had to say whether the two images are the same or not. This was just to control that people do encode the images. And after the response, participants were asked to give their strategies. And we asked people to calculate out loud to have converging evidence of the strategies. So we use this task because we know from previous experiments that in this task, both young and older adults used a large repertoire of strategies. In fact, they used 9 strategies listed here. You see, they can round the first operand, the second operand, both operands down or up, or use columnar retrieval, borrowing units, and direct retrieval. So you can calculate, or you can tally the number of strategies used by each individual under emotion and neutral condition. But first, look at the performance. We do replicate the increased latencies under the emotion conditions here in red as compared to the neutral conditions here in black by 566 milliseconds in young adults and by 413 milliseconds in older adults. These participants solved 96 two-digit addition problems, and there were 29 young and 28 older adults. But look at strategy repertoire. When we calculate the number of strategies used by each individual, in black here you see neutral conditions. You see that young adults use on average 4.7 strategies in the neutral condition, but 3.9 strategies in the emotional conditions. So emotions led young adults to use fewer strategies to accomplish this task. Interestingly, emotion did not change strategy repertoire in older adults. So you see, adopting a strategy perspective can shed very interesting insight into how emotions influence young adults' performance and older adults and age-related differences there. The second experiment aiming at testing strategy selection. So we tested 27 young adults, 33 older adults, to whom we ask to accomplish a computational estimation on two-digit multiplication problems like 34 times 67. They had to give an approximate product by selecting the best strategy among the two available rounding down and rounding up strategy. In the rounding down strategy, people round both operands down to their nearest decades, whereas in the rounding up strategy, they rounded up both operands to their nearest decades. And we had some easier problems and harder problems. Easy problems was easier to select the best strategy, and harder problems it was harder to select the best strategy. The question is, under emotion, are young and older adults equally able to select the best strategy on each problem? Now, on the left side of this panel, you see across all problems in young adults, you can see that the rates of better strategy selection decreases such that in neutral condition, young adults, as has been found before in many previous experiments, they're able to select the best strategy on about 64% of the problems, but they decrease and do so on 58% of the problems. You see the same rate of decrease between neutral and emotional conditions in older adults. So here you can see that emotions led both young and older adults to the same extent to use the better strategy on each problem less often. And this was true, even more so true for easier problems than for harder problems, possibly because they select the better strategy more often on these easier problems. Finally, I ran a third experiment in which I tested the role of emotion on strategy execution, where on this same computational estimation task, people were forced to use the rounding down strategy on the first set of 48 problems and the rounding up strategy on the second set match 48 problems for half the participants, and the other half saw the reverse order under both neutral and negative emotion condition. So here's the solution times. The errors and percent deviations show the same patterns. You see overall here, young adults and older adults increase their latencies under emotion condition. What is interesting here is that the effects of emotions in young adults and older adults interacted with the strategy such that in young adults, they increase their latencies under emotion condition to the similar extent when they executed an easier rounding down strategy than harder rounding up strategy. You see the increase 268, 199. It's not statistically significant. Very interestingly, and this is the last finding, older adults were not negatively influenced by emotion when they executed an easy strategy, the rounding down strategy, but they were dramatically influenced by the negative emotion when they executed more difficult rounding up strategy, increasing their solution latencies by 379 millisecond. If I can give just 1 minute conclusions, we've seen deleterious effects of negative emotion on arithmetic performance, and slightly more so in young adults than in older adults. Most originally, we found that emotions influence strategy repertoire in young adults, strategy selection in both young and older adults to the same extent, and strategy execution in both young and older adults, but modulated by the type of problems. More generally, I think this kind of data improve our understanding of how or whether emotion influence arithmetic performance and how. But of course, I think, like as usual, above and beyond arithmetic, adopting a strategy perspective can shed very important insight regarding how emotion influence cognition. Because in all of this work, usually people claim that emotion influence cognition through general attentional mechanisms, but they don't aim at determining whether emotions change the way we approach cognitive tasks, whether the chain of cognitive mechanisms brought up in a task by participants and by participants of different ages are the same or different. Adopting a strategy perspective enables us to get much deeper insights, because we can see that emotion not only change participants' performance through general mechanisms like attentional mechanisms, but also it changes the way people accomplish tasks or the series of cognitive mechanisms that we use to accomplish cognitive tasks. Thank you for your attention, and I'm open for questions now.
Thank you, Patrick. Are there any questions? Yeah, Marta.
Hi, very interesting results, Patrick. Thank you for that. I was wondering about the first finding you presented with strategy repertoire. The striking thing also is that older adults seem to just use fewer strategies overall, regardless of emotional condition. And so I'm wondering if it's the case that maybe younger adults are using more strategies, but also using perhaps less effective strategies, right? So if thinking about the finding where older adults were less affected by emotion with easy strategies, right? Do you see some sort of differences, or do you think, maybe if you haven't analyzed yet, do you have a sense of, are older adults just picking more efficient strategies and therefore, are less affected by the emotional manipulation?
Well, actually, it's neither way. Actually, so there is a third possibility. They're not using less efficient strategies to accomplish this task. This is why we use this task. However, they use fewer strategies, which leaves smaller room for emotions to negatively impact the number of strategies. So before having really firm, definite conclusions regarding the lack of effects of emotions on the size of strategy repertoire in older adults, I'd like to replicate those findings and extend them to tasks where the strategy repertoire in the neutral conditions can be compared or are the same in young and older adults in order to really know whether they're less effective. Note, however, that in the other strategy dimension, they seem to be less influenced by negative emotions, which is consistent with previous findings in a number of cognitive domains where, especially for negative emotions, older adults are much less impaired on the emotions than young adults, in contrast to positive emotions. So also the next step would be to compare them on positive emotions. Thanks for your question, Marta.
Any other questions? I have a question myself, Patrick. You mentioned the 4 parameters of strategic change, but you didn't tell anything about the distribution of the strategies.
Yes, that was a good point, because actually, when we look at the strategy distribution in the first experiment, examining the strategy repertoire, there were no differences, but I did not report them here because there is a confound between the size of strategy repertoire and strategy distribution. If you use different number of strategies, you may expect different strategy distribution. So in order to more strongly test the effects on strategy distribution, I would need to use a task where both young and older adults are using under neutral conditions the same number of strategies in order to see whether the strategy distributions is effective under emotional condition, both for young and older adults.
Yeah. Okay. I see it's already 6 past the hour. I think it's time to conclude this symposium, and I would like to thank everyone in the audience to be here and for their presence and for paying attention to these 4 talks.
Thank you to all of our speakers today. It was a wonderful symposium. We hope to see everyone next Friday for our next symposium. Thank you all.
Bye.
Bye.